I'm Edward, and I'll be taking you through this presentation on why resolution matters. In particular, I'll be looking at some of these remote sensing applications, and the examples that I'll be demonstrating is going to be based off of the utility of some of our instruments, which we will classify here as high resolution and ultra high resolution. Just going over the general outline, I'll be addressing briefly what is spectral resolution and what that represents in its role in remote sensing, followed by some of the challenges that is presented now with an evolving technology. And then I'll get into a brief bit about our instruments, and then some of the examples I'll get into for vegetation, the mineral soil analysis, and then any radiance measurements that I took here at Haverhill, Massachusetts. And this will be looking at two different instruments, as I mentioned earlier, between the high resolution and, as I classified, the ultra high resolution spectrometers. So what is spectral resolution? Essentially, in its simplest terms, it's the spectral resolution of a system that it can determine the maximum number of spectral peaks that the spectrometer can resolve. Though this could be determined as one of the most important characteristics of a spectroradiometer, below I've listed off that it's not limited. A spectrometer's ability is not limited to its spectral resolution, and some of these other considerations to have in mind when you're looking for a spectrometer is the optical design, some of the sensitivity, the signal to noise levels. Some of this information is vital and key when you're determining what type of instrument you might need to acquire the types of data that you need in your desired application. So what is the role of high resolution spectroscopy these days? Essentially, the modern remote sensing technology is developing so rapidly, and there's this trend for the finer or better data sets. And these technologies involve multiple platforms, multiple angles, and multiple type of sensors, as well as multiple spectral resolutions. So on the right, you have a brief, a detailed schematic of essentially these different scales of platforms, and you can see their different field of views and different types of information that they're characterizing. And all of this is extremely important and able to characterize the environment that you're interested in. So high resolution remote sensing data nowadays are widely used. Things are coming online so rapidly, and the information extraction from these high resolution remote sensing data sets is important for all types of research. These data sets also provide effective data to support the detailed extraction of these landscape information, such as the phenomenon that this plane and this satellite and this tower on this right graphic is characterizing. And this type of high-level geospatial data is what's driving further insight into applications, for example, climate modeling. We're getting an abundance of frequent observations of our Earth to help us understand what might be occurring. And then furthermore, we can get even into the finer nitty-gritty of biodiversity, understanding species identification, understanding what kind of leaves or vegetation that are within a specific forest that can help us with understanding even ecosystem functions, and which can lead into even further things on understanding what things to preserve, what not to preserve. And these levels of detail of information is key for policymakers. So the role of the remote sensing is that it's providing us a ton of data coming from these myriad of sensors, and one of these is the optical remote sensing sensors that I'll be addressing today, which utilize the visible, near infrared, and SWIR information to collect spectral characteristics, which feed into those short list of applications that I listed off in the previous example. So it's important to understand that that with this information, targets can be differentiated by their spectral reflected signatures with these differing platforms, such as the drone picture on our right, which is one of our instruments that is being placed on a drone. But from there, you can get a landscape information, but also you can take off the instrument and begin to take down to the leaf level scales or smaller footprints of the constituents underneath that drone. So helping with validation, this allows some flexibility with the use of these types of instruments. And as they begin to get integrated into different platforms, this is becoming even more helpful for researchers. Now that we have all of these amazing data sets, there are some of these challenges that are presented, and these approaches need to be considered. When you acquire your data, some of the approaches need to be considered for validation and intercomparison between these technologies and platforms. And this is vital in the field of remote sensing. So on the right, I have that image of the USGS. That provides some information from different platforms and different scales of information. And as we can see, if in the past individuals just rely just on Landsat or MODIS satellite imagery, you kind of get a trend of what some of these characteristics or the spectral characteristics are of your area. But then it's not until you get to these finer scales where resolution actually truly becomes enlightening in understanding some of these other key absorption and reflection features of your substance. So while we have all of these data sets, the thing is that they're all derived from various initiatives and with different methodologies and standards. So they often lack that comparability in accuracy assessments. So in order to validate and integrate many of these data sets, this relies heavily on data sources that are at a finer scale, which leads me into some of the finest scale information that you can get in the field of remote sensing. These are our spectroradiometers, and these are one of the ways of doing some validation or ground truthing, as Nicholas mentioned earlier. But these are the two of several spectral evolution instruments that I'll be describing today. These are both field and lab portable instruments. The one on the right is what we consider the PSR Plus, which is one of the what I'll classify here as the high resolution instrument, which we manufacture. Both of these in Haverhill. The PSR Plus has some specific features that are a little different than the SR6500, which allows it to be a little bit more field friendly, but the 6500 is easily as operational in the field as the PSR Plus is. So the 6500 on the other hand is what I'll consider in this webinar as the ultra high resolution spectral radiometer. And what makes this instrument so unique is that it is the highest resolution field operational spectral radiometer currently on the market, with a spectral resolution of 1.5 nanometers in the UV vis and 3 nanometers for the SWIR-1, as well as 3.8 for the SWIR-2. So again, I'll be instead of using the traditional names, I'll be utilizing their resolution standards as their titles going forward. So with some key differences between these instruments, as you can see here, are these detectors. And this is what actually makes them, what differentiates one from the other and allowing for the spectral resolution to be possible. So some of the examples that I'll be going over in this webinar is the way that I use these instruments. I went through a few applications with vegetation in the soil and mineral, and taking some irradiance measurements out here in Haverhill from these two instruments. In these examples, I'll be highlighting the necessity for high resolution to reveal some key spectral characteristics in these samples that I've taken. One thing to keep in mind is that not all applications or research require such high resolution. And there are times where utilizing an ultra-resolution spectroradiometer isn't always necessary. So depending on your application, it's always good to take these into consideration because you actually won't provide any additional benefit to your data potentially, but you'll be spending a lot more money. So the first application is this vegetation example. And one that I'll be focusing on heavily is the invasive species detection and monitoring in particular. In this example, we have a hemlock woolly adelgid infestation, which is a tiny insect that is causing widespread death and decline to hemlock trees in the eastern United States. The most obvious sign of the hemlock woolly adelgid is this covering of wool-like wax filaments that are produced as the insect matures. So you can kind of get a good picture of this at the top right photograph of where you have the twig of the hemlock. You have some of the needles, and then you see those little white pockets there, which represent the hemlock woolly adelgid mature infestation. The uniqueness about this infestation is that the only time that they're most evident is during the spring and fall seasons. So you would really have to be able to time it well to be able to visually see it during these times, or else you would have to wait maybe years down the road as the hemlock tree declines or the thinning of the canopy occurs, which is difficult for some of these ecologists to gauge until it's heavily infested. So here is some of the data collection that I used for this analysis. The two instruments, of course, I used was the PSR Plus and the SR 6500. But when I had an opportunity to get out into the field with one of the ecologists, I realized that these were pretty small infestations to take a look at, and it really required some precision in order to get these measurements. So after I went to the field and I was able to bring back some of the samples to the facility to take measurements, there was this challenge of being able to tease apart some of these spectral signatures between the twig, the needle, and those woolly filaments. However, the use of this precision probe, which can be seen in the lower left picture here, was used in order to identify key constituents within my field of view. And the uniqueness of this probe is that it actually has a 1 millimeter footprint, and this was used with both instruments, so they were both able to acquire the same exact area that I wanted to observe. So here are some preliminary data from these scans. On where you wouldn't see much variation is at the top in the spectral information between the ultra high and the high resolution instruments within the hemlock needles. So I just ended up putting up one of the scans just to give the users, the audience, an idea of the types of results that you could get from the precision probe in particular. Down at the bottom, you have these little wool sacs that I actually extracted from the twigs and took them off to be able to get just these spectral responses in particular. So since that precision probe can concentrate on these very small samples, I was able to gather some distinguishing spectral characteristics of those wool portions. You can see the red spectra is displaying the ultra high resolution scans, and the green line is the high resolution scans. Both of these were able to characterize these key absorption features within these wool sacs pretty nicely at about the 1731 nanometer range, as well as the 2200 nanometer range. So these were the types of spectra that I wanted, these types of absorption features that I wanted to be able to observe going forward. So now I wanted to take a more representative sample. So here's a display of several features. The one on the top is the wool sac in the blue that I just took from the other scan, where you can still see those absorption features at the 1731 nanometer range, as well as the it's about the 2300 nanometer range. Leaving that there, it kind of gave me an idea to where I wanted to find perhaps some of these spectral characteristics when I took a more representative sample, which is down below. So where the instrument's field of view would capture some of the needle, the twig, and that branch is kind of more of how down the road I wanted to be able to take these samples at a distance, and seeing if there's a way that once this field of view becomes more, I guess, more infested or less infested, hopefully I would be able to classify some of these absorption features at the 2300 mark. So the contribution down below from the ultra high resolution instrument provided this insight into the hemlock woolly adelgid features. So this is in the red line at that 2300. You can see where there is a slight absorption feature there that helps characterize perhaps some of these hemlock woolly adelgid presence on these twigs. As for the other green, just the high resolution, this was a little more muddled there, where you couldn't be able to differentiate between that and the other constituents that were within the sample. So moving forward, these were just the samples taken in the lab, but what I'm planning to do is another trip to take some canopy measurements at the same location with the ecologists and help in finding areas with different levels of infestation to see if we can actually capture or characterize these infestation levels. So needless to say, these infestations for the hemlock woolly adelgid is hard to see with the naked eye. So sometimes these ecologists have a very difficult time. But if there are locations where we can utilize some of these higher resolution instruments, these ultra resolution instruments, to be able to characterize this infestation, will help with providing some management as well as progression monitoring for these hemlock sites. So moving forward, I'm going to jump into the soil mineral example. And the particular sample that I'll be using is the kaolinite mineral that we have here in-house. In terms of soil analysis, identifying and distinguishing different clays within soil is a popular application. As kaolinite clay occurs in abundance in soils that have formed from chemical weathering of rocks. So due to this, clay minerals that look very similar from the spectral perspective can benefit from higher resolution, where information can be misinterpreted for something like illite or smectite samples. Kaolinite in particular shows additional features with ultra resolution that are not present with the high resolution spectroradiometer, which I'll showcase in a moment. So here we have our data collection method for this example, which I utilized our contact probe. It has a 10 millimeter spot size, and it has a tungsten halogen light source in it. So you can easily connect these to the instrument, and I use these with both of the PSR Plus as well as the 6500. Here are just two of the scans from the ultra high resolution and from the high resolution, where you can't see much on a visual inspection of any variation. But one thing that you can see slightly is at this 1400 nanometer range, where you can see some delineation between the two scans on the same sample. However, once you zoom in, as you can see in this picture here, you can see some of the key features of the kaolinite sample. one can begin to tease out some more detailed information. And in this zoom, you can see the red line is a kaolinite sample taken of the high spectral resolution instrument. And the green line is the sample taken with the ultra high resolution spectrometer. As you can see, the ultra resolution spectra shows additional features that are not present in the high resolution spectra. And the additional features in the green line are due to the stretching of the OH overtones in the kaolinite sample. So as I mentioned before, the ultra high resolution is important when distinguishing between different minerals in soil that may look similar from a spectral perspective. And then finally, one of the other examples that we went through is a solar irradiance example. And this has significant implications to remote sensing, as most radiation detected by passive remote sensors passes through the atmosphere. And I think many might be familiar with this diagram on the right on understanding how the incoming energy interacts with our atmosphere and what ends up happening when it reaches down to the surface. So knowledge of the spectral distribution of the solar radiation is crucial in interpreting the radiative process in the atmosphere and the surface. So the data collection that we used here was an inline diffuser that attaches directly to the end of the fiber with each of the instruments. And then on the right, you can see the cloud conditions that I ended up having when I took the measurements. It was a beautiful day in Haverhill, and you could hardly see a cloud in the sky. So it provided for a great day for taking some irradiance measurements. So here are some of the data retrieval from the two instruments, and what can clearly be seen on some of these features in the atmosphere are the ones that some people are familiar with: the O2 bands, the H2O bands, and the CO2 bands down further into the SWER2. Again, similar to the kaolinite, based off of visual inspection here, there isn't much that could differentiate the two, but when we delve in a little bit deeper into some of these bands, we can see some of these contributions from the ultra high resolution and the high resolution and seeing these differences. So in this slide, we zoomed into the feature of the O2 band. This light blue spectral line is the data coming from the high resolution instrument, and the red data coming from the ultra high resolution data. And in this O2 band, you can see some increase in the depth of the absorption, but also the interaction between the energy and the constituents within that region, which is not well defined within the high resolution instrument itself. Then we can look down below at this H2O band scan where we zoom in on this region, and you can also see further interactions between the two scans, where some of this is muddled with the high resolution in light blue the instrument, but not in the ultra high resolution instrument. So in conclusion, based off of some of these examples, I hope to address or show how resolution can matter when deriving or wanting to observe key spectral features that were otherwise obscured, in particular with the invasive species monitoring. I haven't come across any literature as of yet describing these features of just the woolly signature at this 22 or 2300 nanometer feature. So we're going to continue to take some more measurements this fall to be able to see if we can characterize this further and see if the utility of this ultra high resolution instrument can provide further insight, hopefully, for these ecologists. Furthermore, for the soil and mineral identification, the ultra high resolution, as I mentioned before, was able to help with furthering the delineation between clay minerals, because sometimes there are these subtle shifts in these spectral bands at the 1400 nanometer range that that can only be classified with an ultra high resolution instrument. And finally, with the irradiance measurement, this need for the higher resolution or the ultra resolution information provides a higher level of information on the interactions in the atmosphere with a field portable instrument. So this isn't just something that you install out there and you leave over time. This can be something that you can have interactive with your other applications to help with other data retrievals that you'll be gathering from either canopy measurements or some other soil analysis as well, where you need some of these irradiance information going forward. Here's my contact information. So if anybody wants to reach out to me on any of these applications in particular, or further information about some of these instruments, feel free to let me know, and we can discuss those.